So thanks everybody for coming. I'm excited to introduce Rebekah Aduddell, who will tell us about the critical and co-critical degrees of a totally acyclic complex. Rebekah.
Okay, first I just want to say thank you, Sean and Eloisa, for organizing this seminar. It's been really cool. And then thank you for everyone who has shown up today. So I have sort of three goals with this talk. The first is to introduce the notion of critical degree in the original setting where it was defined, which I'll say, okay, it's the Armad category. And then I would like to present my extension of this notion to the category of totally acyclic complexes, which we denote as KTAC. And additionally, I'll briefly discuss my study of how this extension behaves under operations of complexes. And then third, I would actually like to, towards the end of my talk, argue why this extension is actually not optimal. And then I would like to propose an alternative definition. Okay. So to set the sort of the stage in the original setting for the entirety of my talk, R will be a local commutative ring. With max ideal M, residue field K, and then whenever I refer to like a maximal M, capital M, I'm talking about a finitely generated R module with minimal free resolution, which I'll denote as an F. And whenever I talk about free resolutions of R modules, I'm specifically talking about the minimal free resolutions. And then I'll denote BI as the betti sequence. And so just recall that the ith betti number is just the rank of the free module at the ith degree in the minimal free resolution. Okay, so I'm particularly interested, of course, in infinite free resolutions. And so one question that everyone cares about is, well, when we have an infinite free resolutions, what patterns can occur in the betti sequence? And so, for example, some well-known facts are, one example is when our ring is not a complete intersection, which I'll denote as a CI, then if we look at the betti sequence of the residue field, that eventually has exponential growth. But if we do look at a ring that is a complete intersection, then the betti sequence of the residue field is eventually given by a polynomial. And in fact, we, whenever we look at modules over complete intersections, we see the polynomial growth in the betti sequence. So the betti sequence has nice patterns at infinity. And so to kind of get into the groundwork for a lot of what I've done for my thesis is I've focused on a definition that was originally defined in this paper, complete intersection dimension, by Lucho, Avramov, Gasharov, and Peeva. And I believe it was like many years ago. So I think it was circa 1997. So that was when I was really young and I was not thinking about these topics. But I want to give the main idea of this, and I'm going to try to talk about it in not super specific details, but the idea was there was this notion of CI dimension, which they defined, which was like the main star of this paper. And the idea was to define a new class of modules, which would admit structural similarities in their free resolutions to modules over complete intersections. And so the point is they said, okay, when we look at a module of finite CI dimension, and I'm not defining what CI dimension is, but the idea is it's sort of almost an extension of the class of modules over CIs. But when we have finite CI dimension, basically patterns at infinity do arise in the Betti sequence, right? So the example would be looking at the class of modules over CIs where we eventually have polynomial growth. And so the question that I want to focus on is, well, when do these patterns arise? And so the answer to this question is critical degree. And if CI dimension was like the star of the paper, critical degree was like the guy off to the side of the stage raising the curtain. So he didn't get as much attention, but I would like to give him some attention now. So the critical degree of a module, which we can denote like this, is the least integer S for which the free resolution, the minimal free resolution, admits a chain map of negative degree such that at degree n plus q, that is surjective, right, for all n larger than S. And then, of course, we can say, if no integer exists, set the critical degree to infinity, right? And then for all non-zero modules, the critical degree is always between -1 and infinity, inclusive, and then the critical degree of the zero module is negative infinity. So just to kind of pictorially draw this, right, what we're saying is, okay, if this is like the minimal free resolution here, we look at some, chain endomorphism, and we're saying there's some chain endomorphism on F that would admit a surjection, so say here, right, and onwards, right? So what we're saying is at this point onwards, we would actually see growth in the Betti numbers, and it's right. And so the critical degree would be like the guy directly before that. And so they have this theorem in their paper that says this specifically. So this is in the CI dimension paper. But we're saying, okay, if the complexity of the module is less than or equal to 1, then, and this includes the case of finite projective or finite free resolution. And so in that case, the critical degree would match the projective dimension of your module. But we don't see growth in the Betti numbers. They're just constant for n specifically larger than S. S is the critical degree. If we have complexity of our module greater than or equal to 2, then we see this strict growth. And so what we're saying here is that specifically after critical degree, the Betti sequence has strict grip. And this is for all modules of finite CI dimension. Okay, so because this is telling us where the pattern would start, obviously, you know, it might be kind of a question of, can we have bounds on this? And so I'll just mention this. The authors did give bounds for the critical degree of a module in terms of the depth of the ring and the depth of the module when the complexity was less than or equal to 1. And then they discussed the case when the complexity was 2 in a later paper. I don't believe anyone has looked at when the complexity was larger than 2. But I will say, however, there is no bound valid for all modules of a given complexity, right? So greater than or equal to 2. And so the example they give for this is let me kind of, I think it'd be best if I drew a picture here. So if we look at a module with like critical degree, like say it's 0, so the growth starts like almost immediately, right? Then we could just take a cos as a g, so m prime, right? So then say m is the s plus first syzygy of m prime, right? And, you know, then we would kind of, that difference would be s, and so then the critical degree of m prime would be s in this case. But, you know, clearly the complexity of m and m prime are the same. And so this idea kind of gives some motivation as to why we might want to extend this to the category of totally acyclic complexes and kind of look at, well, as a complex as a whole, can we kind of define this notion of critical degree in that setting? So let's start looking at that setting. And so for the remainder of this talk, C is going to be an R complex. And specifically, it'll be a totally acyclic complex. So what I mean by this is all the R modules are projective. And so since I work in the local case, this means my modules are free in my complex. And then additionally, we have exactness, but then also exactness of the dual, where the dual is CR. And so when I'm looking at a complex of free modules, we can think of this as flipping all the arrows and transposing the matrices. Additionally, I just want to mention that, you know, a complex is minimal if each differential maps into the submodule generated by the max ideal. Okay, so then additionally, every R complex can be written as a direct sum, as you know, a minimal complex. And so when I use the bar notation, I'm usually talking about kind of the minimal subcomplex or an induced map on the minimal subcomplex. And then a trivial or a contractible complex will be the second summon. And so what we mean is the identity is null homotopic. And so let's define the category of KTAC. So KTAC is the category with objects as totally acyclic complexes, and then morphisms as homotopy equivalency classes of our complex chain maps. And so the KTAC is a full subcategory of the homotopy category of our complexes. And so this is the world that we're going to be in for the next however many minutes. But first, I just really want to formalize this connection of totally acyclic complexes to R modules and free resolutions. And so the formal definition that sort of gives us this connection is that of a complete resolution. So a complete resolution of an R module is a diagram. So this diagram here, where that U is a totally acyclic complex. P is just a projective resolution of M. And then the map between U and P is eventually bijective. And so I want to just mention two things. The first is that we have this fact that any finitely generated module has a complete resolution. And so what we can look at is there's a way to construct this using the free resolution of M. And so there's a way to kind of take the free resolution and then create kind of a totally acyclic complex from that, where we have an eventual bijection of that map. And then,
Rebecca?
Yeah.
I'm sorry to interrupt. Are you assuming that R is Gorenstein? I might have missed this assumption.
Yes, I believe so. I mean, I work in a local ring.
Right.
And so I'm not super familiar with Gorenstein rings.
Okay.
So I don't know that I am, but.
Well, are you at least assuming it's a complete intersection then, or just?
So yeah, I should say this. Most of what I care about is when R is a complete intersection.
Because the existence of this complete resolution is equivalent to the finiteness of the G dimension of M.
Oh yeah.
In general.
So then yes, I'm assuming that.
Okay, cool. Thank you.
No problem. So then the second, so the second thing is that we also, for every complex, totally acyclic complex, we have a diagram. Where we can look at the truncation of C at N, and then our module is the image of the nth differential. And so the point is, and before I say the point, I should mention that I'm often going to abuse notation and call the totally acyclic complex the complete resolution. But the point is that we sort of have this connection between, from any finitely generated R module, there's a way to construct a complete resolution, and we actually do this, we can do this minimally, right? And then there's also a way to, given any complex, we can sort of relate that to R modules through kind of the syzygy modules sitting in the complex, or the images of the differentials. And so, you know, instead of really studying kind of free resolutions and the betti sequences, I really study the complete resolutions and kind of what I'll dub the complete, I don't know if this is actually a name, but I'll dub it the complete betti sequences. And so I'm talking about the doubly infinite sequence that we get in the minimal complete resolution of a module. Complete. Okay. So now I want to talk a little bit about the structure of the category that I'm in. And so the KTAC is a triangulated category. And I'm not going to fully define what a triangulated category is, but I'm going to talk about the main structural components, and then I'll kind of set it aside and kind of come back to this later again. But the first main structural component is we have this notion of shifts, right? Or the suspension endofunctor. And the idea is, you know, this functor takes a complex C to shift C. And this is the complex with the nth module being the n minus first module of C, and then differential would be negative the n minus first differential on C. And we could also talk about kind of any degree shift and so on. And so that's going to come up in my definition in a second. Then we also have this notion of a class of distinguished triangles, which I'm not going to define formally right now, but I'll just say for now they are distinguished triangles are like the analog to short exact sequences in abelian category. So KTAC is not abelian. We don't have short exact sequences, but we have a distinct class of distinguished triangles, and I'll define that later on. But for now, let's talk about the sort of the extension that I have, or the first extension that I have to KTAC. And I pre-wrote these definitions out, but they're sort of exactly what you would expect from the definition of, critical degree of an R module. So there are a few distinctions, though. The first distinction is I chose to define relative critical degree, and specifically relative to a chain endomorphism. And so the relative critical degree, so if mu is like a degree Q chain endomorphism, and whenever we say like degree 2, we're talking about shifting the complex to the left. So it's technically negative degree. Then the mu critical degree is the least integer such that the induced map on the minimal subcomplex of C at degree I plus Q is surjective for all I greater than N. And so it's sort of exactly what you would expect. And then if no such integer exists and S is not equal to negative infinity, that's when you would set the mu critical degree equal to infinity. Now, similarly, we're looking at a doubly doubly infinite sequence here. So we have a dual notion of co-critical degree relative to chain endomorphism. And so this is going to be defined as the largest integer such that the induced endomorphism at degree I, right, is split injective, and it's for all I less than N, right? And then if no such integer exists and it's not infinity, then set the mu co-critical degree to negative infinity. So then the main kind of definition is just taking the critical degree of the complex is taking the infimum over all mu critical degrees, and then the co-critical degree is taking the supremum over all mu co-critical degrees. And so then pictorially, I'll kind of draw a little informal diagram here. So pictorially, if we have, say we have our complex C, and we say, okay, we have an endomorphism, degree Q, where we see surjection here and onwards, right? And so then the critical degree would be there, and then we'd see kind of like growth here. And then similarly for co-critical degree, if we have split injections kind of here and onwards, then we'd kind of take the co-critical degree there, and we'd see, and when R is a CI is kind of why I do the growth diagrams, but we'd see kind of growth in the Betti sequence onwards there. And so I'll just note that so if we take M to be the image of the zeroth differential of C, then the definition for critical degree of the complex, like that would agree with their definition of critical degree for the module. And so we did the definition to try to match that. And so then the probably the most important question is, does this definition, so I've called it definition 1, but also the main definition, make sense in KTAC? So what we mean by that is if two complexes are homotopically equivalent to each other, right? Then, are they going to have the same critical degrees, or are they going to have the same co-critical degrees? And this is true. And same for co-critical degrees. And the proof isn't like, it's really straightforward, but it just relies on the fact that when we have two homotopically equivalent complexes here, their minimal subcomplexes will be isomorphic, right? And so we're saying, okay, we sort of have this correspondence, a one-to-one correspondence between endomorphisms on the minimal subcomplex of C and that on D. And that's just the idea of why this statement is true. So we're gonna start getting into this idea of the study that I've done on kind of what happens under certain operations of complexes, but I wanna make two things clear. And so it might already be obvious to you, but if it's not, I just wanna make it obvious. So for any endomorphism on a complex, note that the mu, so if the endomorphism is mu, the mu critical degree, I don't think I gave myself enough room there, I'll write it down here. The mu critical degree will be greater than or equal to the critical degree. And the mu co-critical degree will be less than or equal to the co-critical degree. And so, I mean, this is just making, obvious that we can use the relative critical and co-critical degrees as bounds for the actual critical and co-critical degrees. And so that was kind of one of the reasons why we chose to talk about critical degree and co-critical degree relative to an actual endomorphism. And so then the next statement is, so if we have, critical degree of a complex equals some finite, well, at finite or negative infinity, right, then we're saying there exists some endomorphism that realizes that critical degree. So such that the mu critical degree would be equal to S, right? And so this is also obvious, and then likewise for co-critical degree. Okay, so these two kind of observations basically help us be able to say something in regards to when we start looking at manipulations or operations of complexes. And so this is kind of like a bulk of what I've been focused on, is studying, okay, based on certain operations, can we say anything about the critical or co-critical degree? And so there's three basic operations in KTAC. The first is, we've already discussed it, but this notion of shifts. And then we also have, I'll say kind of summons or taking summons. And so I'll describe what I mean by that in a minute, but then cones as well. And so for shifts, it's relatively easy to be able to say something in this case. For example, the critical degree of C plus 1 would be the critical degree of shift C. And then similarly for co-critical degree. But for summons, so what I mean by summons is we sort of, KTAC is an additive category. And so if we have two complexes A and B in the category, and then the direct sum is in that category. In this case, we would be able to say something. But taking summons means if the direct sum is in the category, then each of the summons is in the category. And that's when it's a little bit more difficult to say something in that case. So we can say something here, but this is a little bit more difficult in this case. The issue kind of being like, okay, if we're talking about a surjection at a particular degree, is there anything that would have the second summoned mapping into the first summoned and like contributing to the surjection and vice versa? And so then the third basic operation is our mapping cones. And so this probably is the operation that I care the most about. And unfortunately, I haven't really been able to say anything yet in that case. But I'm going to come back and actually talk about some of the problems with that. But I will say, okay, so it seems like saying something about the most basic operations in your category would be easier. But actually, that's not quite the case. So we also have some additional operations where I have been able to say something. And so the first is this operation where if you sort of fix a bounded complex and then you define this functor where you tensor with that complex, so bounded complex, then this would again be a totally acyclic complex. And so what happens, I'll just briefly describe it because it's a little bit easier to describe in this case. But like if take like a bounded complex where you have consecutively non-zero modules and call the length the number of consecutively non-zero modules, right? Call it L. And so then what would happen is if we have, so say in our original complex, right, we have sort of the critical degree L. And that would be a bound in that case. The cocritical degree. So then the second operation where I have been able to say something is the pinch tensor product. This is a little bit more complicated. I have used an endomorphism that's kind of difficult to work with. So I'm not going to say what happens in this case just because it's a little bit difficult to describe. But I want to go back to the mapping cone now because that's probably the operation that as I said, I care most about. And so let's kind of explore what's going on with that. So I just have the definition of the mapping cone up here in case anyone needs to be reminded of what each R module looks like and each differential looks like. But basically, the mapping cones help us define the class of distinguished triangles in KTAC. So a distinguished triangle is a sequence of objects and morphisms of the form, and I'm giving this for specifically in KTAC. It obviously generalizes to any, you could write it in terms of any triangulated category, but for KTAC, if we have a chain map from C to D, then the triangle would be made up of the mapping cone of F and then shift C, right? And so this is actually called a standard triangle. Any triangle that is isomorphic to a standard triangle is a distinguished triangle. And so this is what makes up our class of distinguished triangles in our category. So we're gonna get back to this in a second, but the ideal situation would be to say, okay, given a chain map between C and D, and say we know, just assume C and D are minimal and simplest case, and then say we know what the critical degree of C and D is, and then we can kind of also think of this in terms of co-critical degree as well. then the ideal situation is we would be able to at least give a bound for the critical degree on the mapping cone, but situations are not always ideal. And so there's some issues with this. And so I want to outline the two specific kind of issues with this. And the first is actually that we, you don't always, so the process we used when we were looking at kind of the operations, and so like the tensor operations is, hey, the critical degree is realized by some endomorphism, right? Look at the induced endomorphism that you get from the operation, and then use that as a bound for the critical degree. But what happens with this is we don't always get an induced endomorphism. So the case where we would get an induced endomorphism would be, so if we have our triangle here, and then say we're looking at an endomorphism on C and an endomorphism on D, which each realize the critical degree. The question is, okay, they're not going to be, necessarily the same degree endomorphisms, and so we don't even know if we get a map there. But that's how, so this would be like question mark, that's how we would know that we get an induced endomorphism on the mapping cone, right? This notion is if we have sort of this diagram of triangles and that first square commutes up to homotopy, then we would get an induced map on the mapping cone. But let's make our work easier and say, okay, assume Q equals R and the first square commutes, right? So let's assume this is true. Then the question is, so if we get an induced map, say H on the mapping cone, can we now say something? And the answer is no. So the issue here is the mapping cone is almost never minimal, even if you start off with two minimal complexes. And we can't really say what it looks like. So in general, can't say what the minimal subcomplex looks like. So I'll use the bar notation there. Looks like. And so because of this, we don't really know what the induced endomorphism, so I'll call it H bar, is. And so we can't use kind of like the approach we took with the tensor products of complexes. And so, so sometimes it feels like all hope is lost, but all hope is not lost. We have actually started taking sort of like an alternative approach to this. I mean, the first approach was to kind of think of, well, could we somehow say that a surjection on the endomorphism on the mapping cone would imply, kind of what it is on the induced endomorphism. We didn't really get anywhere with that. But the alternative approach would be, so the question becomes, what if we can bypass knowing what the minimal subcomplex of the mapping cone is? And so then the induced endomorphism on the minimal subcomplex. And so the idea is to rely more on the triangulated structure of KTAC. And so I'm going to state sort of a fact about triangulated categories in full generality, but I'm going to use kind of diagram form of saying this. So the fact is I'm in really distinguished triangle, but I'll just keep it simple at standard triangle. Well, any standard triangle will induce a long exact sequence of homology over, and I should say over kind of the triangulated category. And this is for each object in the triangulated category, right? And so this is the fact we're going to use to propose an alternative definition. And so we're going to first denote capital K as the minimal complete resolution of the residue field. Okay, and so this is where I'm using complete resolution kind of informally as the totally acyclic complex. And so then given an endomorphism, mu on C, there exists a standard triangle. So just this guy, right, where this is the mapping cone of mu, and then shift C. And then, so what we get is a long exact sequence of abelian groups. And I should mention, you have one for both the contravariant and the covariant. We're doing the contravariant. So I kind of wrote this out previously, but that's what we're getting. And this is what we're gonna use to kind of propose this alternative definition. And so I have this written out. And so we're changing, definition 2 is changing the way we define mu critical and mu co-critical degree. So we're now saying it's the least integer such that this map of the abelian groups, right, is injective for all I larger than m. And so we're only specifically looking at Hom of shift QC to shift IK and Hom of C to shift I plus QK. I think I said shift IK, but this one should be I plus Q, okay. And then we kind of have the same kind of idea with if no such integer exists and it's not negative infinity, it's infinity, and so on. And then mu co-critical degree will be the largest integer such that we have a surjection on those Homs. And so this, I'll just note this, the sequence of Homs, right, the I's increase that way and they decrease that way. And so when we're going to the right, that's saying for the critical degree now. So at a certain spot going to the right, that's where we would have the injections, and then now going to the left is for the co-critical degree. And so the note here, I'm not changing the main definition.
Do you mind reminding us all what K is?
Yeah, K is the minimal complete resolution of the residue field.
Thank you.
And so then the main definition is the same. So I've only changed the definition for the relative critical and co-critical degrees. So main definition is the same. And so I want to, so the big question is, does definition 2, I'll write it as, does it help? Does it do what we want it to do? So I do want to try to provide a little bit of intuition for this in the last couple of minutes. And so basically what's going on is I should first start off by saying kind of the key idea here is these Homs, I didn't really write it in the definition, but the Hom is with respect to the category. So I'm going to write it as sort of the notation for the homotopy category because KTAC is kind of long. But that's how we're viewing these Homs, right? And so if we look at this Hom, this is isomorphic to if we just look at the minimal subcomplex of C. Since, you know, in the category, C is always homotopically equivalent to its minimal subcomplex. And so this is why it doesn't matter whether we start with a non-minimal complex or we don't need to know what the minimal one is in this definition, right? And so then, so let's just now kind of assume C is minimal, so I don't have to keep writing the bar notation on that. But the next thing, so this was the first kind of note. So the next thing to note is basically, so we have this isomorphism here, where this is going to be isomorphic to the Tate text of the image of the zeroth differential on C and little k. And so I'm gonna briefly, I don't know if anyone needs me to do this, but I'll just briefly talk about kind of what this Tate text is. So it's very similar to, the normal X. The distinction is instead we take a complete resolution of the module in that first slot. And so, hey, a complete resolution in this case is just C. And then you look at the cohomology of Hom R C K. Now, as it turns out in this case, because we kind of took C to be minimal and then K is the residue field, what turns out to be true is that turns out to just be Hom R C I K. And so what I'm saying is we have this isomorphism here between the Hom over the category of the of the complexes and a Hom of our modules. And so then the point is, I want to kind of go back to the definition, or kind of the way we can think of the Betti numbers, even just in the normal case of looking at the free resolution. So recall that this is going to be one way we can define this, is this is going to be the dimension of the ith X of MK, right? And so this notion extends, so this is for free resolution in the normal Betti sequence. This extends to when we look at the complete resolution and what I was kind of referring to as the complete Betti sequence, right? And so this is actually, when we get a surjection and we kind of look at the Homs in this setting like that, we do actually sort of get this connection of those injections are going to relate to an endomorphism that admits a surjection at that degree, right? And that will tell us what we want to know about the Betti numbers and the growth of that in the case of, R being a CI. And so then, the question is definition 1 equal to definition 2? And yes, it is. So, if we look at kind of just, this is a case of the critical degree, right? Where we have sort of an injection here and then we would have it onwards. Well, because of these isomorphisms, the main idea of the proof is just that I use these isomorphisms and do the proof using the Homs with respect to R and the R modules instead. And that's kind of what is used in that case. Okay, so I'll just kind of conclude here. So I want to give kind of this argument of why definition 2 might be better than definition 1. And so there's 2 reasons. So the first hope, I guess I should say, is that definition 2 can be used for, I'll say, kind of like these operations of complexes that don't preserve minimality. And then the second reason is sort of from a more theoretical standpoint of definition 2 really acknowledges and kind of utilizes the triangulated structure of the category we're in a little bit more. And so, I mean, the current thing that I'm mainly looking at right now is basically, this first one of can we use definition 2 to now say something about the mapping cone, because that's really what I'm interested in. So that's all I have. Thank you for hearing me out, and I hope you enjoyed.
Let's thank Rebekah. Any questions? See, I was going to ask about the motivation for using the complete resolution of the residue field, but then you explained that.
Oh, I kind of explained it. I didn't know if I would have time, but I think I did.
So do you have any applications in mind of what you want to do with the critical degree and the critical co-degree?
Yeah, so basically the original motivation for why we defined it is the application we're hoping to do. But it's this idea of kind of being able to compute, like given a support variety, being able to compute a support, the module that has that support variety, but one of fewest possible generators. And so like the idea is, okay, if we can define this middle portion of a complex that kind of is between the critical and co-critical degree, that's where we would possibly find one of those modules. And this process, it's sort of connecting, instead of the module, it's connecting the complex to the support variety. And this process involves taking repeated mapping cones. So that's why I'm actually the most interested in the mapping cone.
Okay, cool, thank you.
So I have a follow-up question. So if I hand you something that I think is the support variety of a module, can you tell me if it is? Maybe this is sort of like, maybe unrelated to what you were talking about, but related to what you just said.
So do you mean like just a support variety of what you think is a module, and then like somehow
Right.
use
Like
this?
I wanted to say, like you were saying, your goal is to maybe build modules that have a given support variety. I'm asking like 3 questions. Like, how do I know something is a support variety of a module? I guess I could go and build it by the process you're hoping.
Yeah. So there's a process where you can build it. So actually build the complex that has that given support variety, right? And so then all syzygy modules in that complex would have that support variety, if that makes sense. And so it's kind of, because you can compute the support variety of a module, but we're talking about going the other way, and then we're talking about doing it because there's already a way to do it, right? But we're talking about doing it where we can identify one with as few generators as possible, somehow using this. But yeah, that's kind of a further out goal right now.
Thanks. Maybe I'll ask you more about this during tea.
Okay.
Other questions?
Yeah, do you have examples of modules without like finite complexity or finite CI dimension that have finite critical degree or finite co-critical? I mean, like, do these things kind of show up? Or? So
I'm not sure. So I'll admit this. So computing examples isn't that great. So this is something we're also currently working on, because there's a way that you can compute it in that they describe with the module, and they actually wrote Macaulay code for this. But then we haven't been able to get that code to work. And so then like even just computing the critical degree specifically for a complex is kind of definitely a weak area, and something that we're working on. So it's even in that case, yeah, I don't even have good examples of like at all, really. We can say something in the case of like a complete resolution of the residue field, and that's probably at most what we could do right now.
Cool. Yeah, thanks.
All right. Thanks again, Rebekah.